So far we have considered the electroosmotic flow in channel in which the surface charge density or the zeta potential are constant. Now that may not be always the situation because of several fabrication law or chemical depositions and several other factors. We may have a situation where the zeta potential or surface charge density may become a heterogeneous one. So instead of a uniform or homogeneous situation of the surface condition, we may have a heterogeneous zeta potential. So say now we will consider a situation where the electroosmotic flow is considered near a surface charge heterogeneity. Now the surface charge heterogeneity will create a characteristic change of the electroosmotic flow. Now we know the electroosmotic flow is basically governed with the direction and magnitude are governed by the surface zeta potential, or in other words the surface charge density. Now if you have a different surface charge density, so we will have a different form of the EDL, electric double layer, and in that process we may have a situation where the flow may not be only the axial direction or only the unidirectional flow. We may have a two-dimensional flow may develop, and also we may have a recirculation vortex formation, and the pressure drop that will be generated because of the different nature of the electric double layer, that may be a significant one. So in other cases where we have taken the homogeneous surface conditions, so we will have only the unidirectional flow. That means the flow along the direction of the applied electric field was the most significant one. But because of this heterogeneity, we may have a situation like this. So see this local recirculation of the domain. Now this has advantage. Now the surface heterogeneity sometimes is also generated because of this formation of recirculation and the induced pressure development and other things. Now what happens is that if you introduce electrodes on the surface, along the surface, so what will have a different form of the zeta potential. That means a step change in zeta potential. Like in the diagram, what it is showing, that you have in some portion a positive zeta potential, and remaining portion we have a negative zeta potential. Now this positive zeta potential will introduce a flow which is opposite to the direction of the flow which has been induced by the negative zeta potential, and in that process we will have a recirculation zone development. So we will briefly talk about one such situation. So what we consider here a single heterogeneity, so that means a kind of patch we can call as a potential patch. That means you have a long, infinitely long microchannel with homogeneous zeta potential everywhere except in a portion where the zeta potential has a abrupt change, that is a step change in zeta potential is occurred, and we consider the microchannel length and width are quite larger than the height of this microchannel. So in a way this is a planar electroosmosis will develop, but because of this heterogeneity of the zeta potential we may have a two-dimensional flow configurations. So that is the thing we will be discussing now. So for the sake of simplicity, we considered a binary electrolyte that dissociate into two equally charged ions, that is a Z-Z electrolyte, 1,1 electrolyte Z and minus Z other valence, and all these things. Zeta potential is taken to be a constant one. Of course, we are not putting any restriction on the magnitude of the zeta potential, but on the homogeneous portion we have a constant sign of the zeta potential, whereas in the patch which has got a reverse or change of sign in the zeta potential. Now, the governing equations, again these are based on the conservation principles as we have described before. The transport of ions are governed by this Nares-Planck equation, and this xi is the concentration of the ionic species I, and here again we are taking a symmetric ions. So basically we are considering a cation and anion, but since we are considering Nares-Planck, so we can have multivalent ions or number of more than 2 number of ionic species. Now, so that means the valence can be a fractional and other situations, and the electric field is governed by that usual Poisson equations for electric potential, and the we assume that the electric field which is externally imposed is constant electric field. So we have the total electric field given by this way, minus E0x plus phi. Phi is the Debye layer potential, or one can say the induced potential induced by the charge density. So of course, this E0x satisfy the Laplace equation. External electric field will always satisfy the Laplace equation. So in other words, this phi, capital Phi, satisfy the Laplace this Poisson equation. So that means if I replace by this, so these equations will be same for capital Phi as well as the small phi. Now the momentum transport equation are given by this way. So here we have considered the first equation is the equation for continuity. We are considering the 3 Cartesian coordinate u, v, w, and these are the momentum equations in non-dimensional form, and the 2 parameters which characterizing the geometry of the problem is, one is that b, which is h by l, height by the length, and c is h by w, the width. So both now what we are considering here, see if I just go back here, since this zeta potential has been changed, so it has got a effect up to certain extent. So let us call the boundary we impose to inlet and outlet boundary x minus L and x plus L, beyond which the inhomogeneity of the zeta potential has got no effect. So that means our computational domain or the domain of investigation for x is between minus L to L. So beyond this domain we do not have any impact of the inhomogeneity of zeta potential on the electroosmotic flow. In other words, the inlet and outlet we can consider beyond this, that is for x greater than L and x less than minus L, we can impose the flow to be a fully developed electroosmotic flow that is governed by the previous equations which we have described. So now, so now this parameter c, which measures the height by width. So obviously we are considering width is much higher than the height. So c is many times less than 1, and the length scale L is equal to here 2 capital L. So here the length scale we have taken L as 2L. So that means x star, the well, here it is x, so let us call this x equal to x star by this L. This is the length scale. This is a non-dimensional variable. Y we have taken as y star by W. Z, what was the length? So this is h, y by h, height, and z by z star by W, because this y is along the height of the channel and z along the width direction, and x is the along the length. Okay, so if I go by this kind of non-dimensionalization and usual things, phi by phi 0 scaling. So we are talking about scaling. So phi by phi 0 the thermal potential, and u 0 for the velocity scale for u, or u v w are the three components. So that means u 0 is the velocity scale, u 0 is the corresponding velocity, the Smolchowski velocity. So u 0 we have taken as epsilon e phi 0 e 0 by mu. This is the velocity scale. So now if I do the non-dimensionalization and we get this equation, this set of equation, and here there is a another parameters, non-dimensional parameters involved, that is called the Reynolds number. So REHS in this case, because REHS the notation, because this is based on the velocity based on the Smolchowski velocity. So this is basically u0 h by nu is the velocity. So this is the velocity is based on the Smolchowski, so that's why this is the Reynolds number. So this is Reynolds number, and another quantity which will come out, because the Speckle number we have already introduced there. So Speckle number, that corresponds to RESC. SC is the Smith number. So Smith number. So Smith number basically comes through that diffusivity of the ions. So this is nu by d. Here we have taken the diffusivity to be equal for all the ions. If we do not assume that, no harm, we will have different Speckle number, because Smith number will change. However, this is remain constant, and this is the P is the Speckle number. Now, usually Reynolds number will be very small in the electroosmotic transport, but this Smith number may not be, because of this d, nu by d, this becomes a large quantity, comparable quantity, and so that way this Speckle number, though this RE is very small, but SC is high, so RE can be P can be of order 1 situation, even if RE is here, of course REHS to our notation, RE may be of many times less than 1. So that is the situation. So that's why the convective transport of ions are not negligible in all the cases, though one can drop these terms, because this convective transport of convective terms or inertia term in the Navier-Stokes equation can be dropped, and it can be taken as a simple Stokes flow, because these REHs are generally very small. Now G and F are the non-dimensional form of Xi. That means we have scaled the ion concentration by the bulk ionic number. So this is the scaled concentration of positive ions and this is for the negative ions, and this G minus F is the scaled net charge density at any point we are considering. Obviously, if we go much away from the Debye layer, so G minus F becomes negligible. And so the non-dimensional form of the Nares-Planck equation comes to be this form, and this is the equation for which is referred as the Poisson equations, and this corresponds to the electric field. So we have now obviously the C is a very small, and C square and C terms can be neglected. So that means we can drop all the gradient with respect to Z. Wherever the C terms is appearing, so we can drop that C terms because of the condition that the width is much higher than the channel height. So basically what it turns out to be a set of partial differential equation for two-dimensional flow. So that means we can write the reduced set of equations this form. So the reduced governing equations are that is uv and all not equal to uv are function of xy only. So one can write this del u del x plus del v del y equal to 0. Similarly, we can have this momentum equation is u del x plus minus kappa h whole square by lambda minus lambda plus del phi del x. This is because you have the component at G minus F. And similarly, the V momentum equation that you can write, and the distribution of ions are governed by this is positive ions governed by this advection diffusion equation. This is P u del G del x plus V del G del y minus del G del x minus lambda plus del phi del x plus kappa h whole square G into G minus F equal to 0. And likewise, we can find out the equation for F and so on. So if we consider a channel of height say h equal to 10 micrometer and zeta is 1 and the over potential or the patch potential as zeta p is minus 1. So what we can find out that u0 based on the Smolchowski value is, that is u0 equal to epsilon e e0 phi 0 by mu comes, and the Reynolds number in this case comes to be 1.5, approximately 1.5 into 10 to the minus 3, and the E0 we have taken as 10 to the 4 volt per meter. So I'll quickly show some results for the homogeneous zeta potential situations. Okay, now these results obviously show a formation of recirculation zone near the. So see, this is the region of heterogeneous zeta potential, region of heterogeneity, and that is inducing a vortex near that. And as we move away, the flow becomes a unidirectional flow, a parallel flow. So this is very advantageous in several situations, particularly in mixing of solute in the nano channels and or micro channel where the turbulent is absent. Okay, there is no chaotic mixing because of the low Reynolds number. We don't have any chaotic mixing in the this kind of micro channels or nano channel, but by imposing the surface heterogeneity, one can get a recirculation vortex development, and that improves the mixing. And this is the vertical velocity, so it is not very insignificant if we consider near this region -1 to 1, where the heterogeneity is appearing, and there is a reversal of the flow is quite evident, and formation of vortex is quite assured by the profile V. So this is about the heterogeneous zeta potential. One can consider a periodic array of zeta potential heterogeneity to promote mixings and all. Now we'll conclude the situation, the microchannel flow, by discussing something on the now here before that some importance of these, why we need a vertical flow development. Something is stated over here. Electrostatic force. Now one thing is that the electrostatic force, which is the generating the flow, will be different when we have a zeta potential step change in the zeta potential, heterogeneity of the zeta potential. Now we come to the situation where we can have a higher rate of transport. That is the one biggest question in the microchannels or thin channels, that because the surface area is quite larger compared to the volume. So that's why we would like to do some modification of the surface so that we have a higher transport in a thin channel situation. So one of these is the hydrophobic surface. In the hydrophobic surface, how we define is that, now basically the hydrophilic or the zero slip boundary condition, what we normally use in a macro scale, is basically a average situation. So that means we assume that the whole solid body or the interface are wet. So suppose we are considering a flow past a surface, solid surface. So now when we talk about the no slip condition at the interface between the solid and water or the liquid, so we assume that the solid is totally wet. Now when we talk about the microscale and all, so there can be a defects or the inhomogeneity in the surface structure. Now those structures or those indentations can be filled with air bubbles, and that create a less friction compared to the, if we have a situation where the solid liquid interactions are occurring. That is the interface between a air and a liquid, and an interface between a solid and a liquid. So in the latter case, we have a frictional shear stress is quite higher. So that's why sometimes even the surface are structured to generate intrinsic slip. So if we have a reduction in the friction or shear stress at the solid liquid interface due to the velocity slip, so what we have a enhancement in fluid transport, because the momentum loss due to the friction will be reduced. So these kind of things are very applicable in fluid transport, pressure driven flow and all. Say I show the situation. Say suppose how the intrinsic slip develops. So suppose we have a channel, thin channel, so which is enclosing a water and a thin layer of gas, say air, okay, and in between you have a water are placed. Now so here we considered a center line in the channel, so that means whatever the mirror image, whatever the flow over here and the flow above the other portion is, other half is the identical. So we are now considering this is the wall, solid wall, above which a gas is situated, and then water. So we impose the boundary conditions can be imposed like this way. At the center line you have no shear, that is du dy equal to 0 at the center line over here because of symmetry, and at the solid gas interface you have the velocity to be 0 velocity, and on the interface between water and gas we have a continuity of the shear stress. This is the shear stress continuity and the velocity continuity. Mu A and mu W are the viscosity of the air and water. Now we assume that the flow is Stokes flow, that means a linear flow. So if we consider a pressure gradient dP dx is applied along the length of the channel, a constant pressure gradient is applied, kind of Poisson flow. So what we can solve and get the velocity distribution in the water, within the water zone, the velocity distribution is governed by this equation. Now at the interface between the water and air, so if we consider the u and del u del y a relation between the u and du dy by this manner, a beta, then what we can find that beta comes to be the formed like this way. So that means this beta, which becomes a slip length. So that means the u is no longer 0 over here, and the friction du dy is low, and it is determined by this factor beta. Beta is depending on the ratio of the viscosity between the air and water. Now, so this will give a enhanced transport in the pressure driven flow. Now the same thing we want to do in the electroosmotic flow. Now if we have we can define this slip length by this manner. So that means uy at h, y equal to h is the slip plane. So we put like this way a relation between the shear stress and the tangential velocity. So if it is a super hydrophobic, that means if we have du dy equal to 0, so then this is the case is the super hydrophobic, that is no shear stress vanished, and the slip length can be defined in this manner. Now we'll just a simple example we'll consider why the super hydrophobic EOF through a super hydrophobic situation is important. Now consider the situation where the electroosmotic flow EOF for thin Debye layer over a hydrophobic surface. So you have a surface, say potential is phi equal to zeta, and the Debye length is quite small. So this is the kappa is the lambda inverse, which is quite large, and so outside the Debye layer, the flow and let E0 be the applied electric field tangential to the surface. Tangential to the surface, which is governing the electroosmotic flow. So outside the Debye layer, the flow is basically the valence between the d2y dy2, this is the momentum equation, and balance between the viscous force mu d2y dy2 and the minus rho e E0. Okay, and rho e is the charge density. So rho e is governed by the charge density, and rho e equal to minus epsilon e d2 phi dy2. This is nothing but the viscous shear stress or viscous stress, and this is the electric body force, so they are balanced. That is, if we have the consideration that there is no other external mechanism to generate the flow. Now, if we assume that ions satisfy the Boltzmann distribution, so we can find out, we can write the form of phi as epsilon e d2 phi dy2 equal to 2 c0 this is f sine hyperbolic f phi by RT. Now, if I apply the Debye-Huckel approximation, so this becomes d2 phi dy2 equal to 2 c0 f square by epsilon e RT equal to phi by lambda square. Lambda is this Debye length, epsilon e RT by 2 c0 f square. So this is the Debye length, and we can write the conditions. So if I say phi equal to 0 on zeta equal to 0, phi equal to 0 at y equal to 0, phi equal to zeta on y equal to 0, that is on the slipping plane. So what I can write is phi equal to zeta e to the power minus kappa y. So this gives you the momentum equations, whatever we are discussing here. So we can write now the momentum equations as d2y dy2 equal to epsilon e zeta e0 by mu kappa square e to the power minus kappa y. Now this is the velocity scale, UHS equal to minus epsilon e zeta e0 by mu. So this is nothing but these equations comes to be d2y dy2 equal to kappa square minus UHS e to the power minus kappa y. Now, what are the conditions we can impose over this is that u at on the slipping plane, u equal to given by this way, y equal to 0, y equal to 0 is the slipping plane. And far away from the wow, that is y tends to infinity, du dy is tending to be 0 because the velocity gradient vanishes. So with that, what we can find, if I just integrate once, and we get du dy equal to UHS kappa into kappa e to the power minus kappa y, because the constant of integration vanishes. At y equal to 0, if I apply these conditions, so what I get is u equal to minus UHS e to the power minus kappa y plus b. And at y equal to 0, we apply the slipping condition, and from there we find that b equal to UHS into 1 plus beta k kappa. So what I find is u is basically UHS into 1 plus beta kappa minus e to the power minus kappa y. So this is the form of the velocity. Now obviously in the previous cases, what I found that velocity outside the Debye layer is UHS. Now here, if I assume when we go for ky tends to infinity, so as kappa y tends to infinity, so u is becoming UHS into 1 plus beta kappa. So that means an amplification of the Smoluchowski velocity is evident. Now, if I write what is the form of UHS, that is becoming epsilon E E0 by mu zeta 1 plus beta k. So, in other words, we can say that the slipping plane enhances the to possess an enhanced zeta potential as zeta into 1 plus beta kappa. So, this is the advantage. So, that means our velocity is quite enhanced in this situation. So, now this movie, see, we have how to make the slipping intrinsic slip effect. So, what I do is in the channel we make the group in a periodic arrangement. So, through that, so if I just play once more, so there is a channel, we have a periodic arrangement of the groups, and this is the group is enclosed by the air. So, what you find that this is immiscible liquid. So, between these two we have a free surface interface formation, and that generates a slipping effect, and we have computed, and what I found the quite significant enhancement, particularly when the Debye length is low. Sorry, Debye length is high because kappa h is low. So, this is the ratio between the ordinary planar UF and this modified, that is with the super hydrophobic. So, what I find is quite sometimes like more than 4 times enhancement is occurring when we have the placing the groups within the channel. So, that means intrinsic slipping effect is considered. So, that is why the super hydrophobic and hydrophobic surface and in the microchannel situations are quite important. So, I just gave some introduction how it works or how the transport can be enhanced by considering a hydrophobicity at the wall. Thank you.